It's an honor for me to introduce Professor Niccolò Guicciardini. Niccolò Guicciardini was born in Florence in 1957. He teaches history of science at the Università degli Studi di Milano. He holds degrees in physics, specializing in particle physics, and philosophy, specializing in the history of logic. He obtained his PhD in 1987 under the supervision of Igor Grattan-Guinness from Middlesex University. His research has focused on the mathematical work of Isaac Newton and its reception in the 18th century. He is the author of The Development of Newtonian Calculus in Britain, Cambridge University Press in 1989, Reading the Principia, the debate of Newton's mathematical methods for natural philosophy from 1687 to 1736, Cambridge University Press again, Isaac Newton and Mathematical Certainty and Method by MIT Press, MIT Press in the 2009, and Isaac Newton and Natural Philosophy Reaction book in 2097, also with a Chinese translation in 2023. He edited the collection of essays, Anachronisms in the History of Mathematics, essays on the historical interpretation of mathematical texts, Cambridge University Press. He has twice been visiting professor at the California Institute of Technology, professor invité at the Observatoire de Paris and at the Université Paris Denis Diderot, Gastwissenschaftler at the Bernoulli Zentrum in Basel, and visiting fellow at Clare Hall, Cambridge, UK, at Peterhouse, and so on. The list is very long. And he was section lecturer at the International Congress of Mathematicians in Madrid. He was awarded the Francis Bacon Award in the History of Philosophy of Science and Technology at the California Institute of Technology, the Fernando Gil International Prize for the Philosophy of Science, and the Sarton Medal. He was co-editor-in-chief of Historia Mathematica. He has been elected non-resident corresponding fellow of the Accademia delle Scienze dell'Istituto di Bologna, classe di Scienze Morali, and life member of Clare Hall, Cambridge. The title of his lecture is Newton's Mathematical Networks. I invite Professor Guicciardini, and the room is yours. Thank you.
Thank you very much, Flavia, for your laudatio. And I would like, of course, to begin by thanking the Vice Chancellor, Professor Calcagnini, for his presence, and the Centro Urbino La Prospettiva and its director, Professor Sorini, the Centro Interuniversitario di Ricerca in Filosofia e Fondamenti della Fisica, and its director, Professor Tarozzi, and the awarding committee for, awarding me this medal. The list of recipients is really intimidating, but I should not be. We should leave intimidation aside and give you a talk, which is supposed to be a 60 minutes talk. So, dear friends, thank you very much. So in this talk, I will present ideas inspired by my collaboration with Scott Mandelbrot over the past few years. It all began in 2018 when I was a visiting fellow in Peterhouse. You can see here a nice picture that I made, and I am quite proud about that. The purpose of my stay in Cambridge was quite straightforward. Scott and we had to produce brief descriptions of the items forming the Portsmouth collection, a vast and well-researched body of Newtonian manuscripts held at the Cambridge University Library. The images of these manuscripts are now online and Hugh Jones and Katrina Dean of the Cambridge Digital Library. You can see here the site of the Cambridge Digital Library devoted to Newton manuscripts, wanted to create a guide for the internet users. And Scott and we produce brief descriptions of these items, you see. Now, this commitment soon proved to be less straightforward than we initially thought, despite the large amount of first-class research that had been devoted to the Portsmouth collection by the likes of Tom Whiteside, Mary Boas Hall, Rupert Hall, Sam Westphal, and Bernard Cohen. In fact, we were somewhat dismayed to realize that many of the hands that you can find in the Portsmouth collection were not Newton's. Why were manuscripts whose authorship we struggle to identify included in the Holy Grail of the Newtonian manuscript corpus? Rather than studying Newton himself, we had to familiarize ourselves with the works and professional status of lesser known mathematicians such as William Jones, St. John Hare, Michael Derry, and James Wilson, as well as better-known figures such as John Collins, Isaac Barrow, and Roger Coates. What we were confronted with was the fact that the Portsmouth collection, as well as the related Macclesfield collection, now also online, revealed that Newton was not, as Wordsworth's somewhat hallucinated image of him would suggest, quote, a mind forever voyaging through strange seas of thought alone. But rather, Newton was an active member of networks of mathematicians who consulted, collaborated with, and rivaled with him. For example, a notebook such as additional 3960.1 shows that Newton mathematical manuscripts were copied and shared within a network of mathematicians who left traces of their presence in Newton's archive. So what we see here is, it is the first manuscript that I consulted when I was in Cambridge. I asked for the box entitled Fluxions, and the first item in this box was a mystery. It is not in Newton's hand. It is not in his amanuensis hand. We discovered that it is in James Wilson's hand. James Wilson was a friend of Henry Pemberton, the editor of the third edition of the Principia. And James Wilson is copying a manuscript that Newton penned in the mid-1660s. It is a manuscript related to the discovery of the calculus, let us say so. On the back cover of this manuscript, you find that William Jones found this manuscript in Mr. Raper's papers. And this Mr. Raper's was copying from a Mr. Watkins, a scholar of William Jones, the librarian of the Earl of Macclesfield, who, the second Earl of Macclesfield, became president of the Royal Society. This manuscript is an example of the fact that Newton's works circulated within networks of mathematicians. So there is a social dimension in Newton's intellectual biography, a dimension that has already emerged in recent monographs by Rob Iliff, Jed Bachwald, and Morty Feingold on religion and chronology, and is particularly evident in Bill Newman's book on Newton, the Alchemist. However, a study of the social dimension of Newton's intellectual biography as a mathematician is still lacking. The problem that Scott and I encountered with the manuscript held in the Portsmouth and Macclesfield collections, as well as the numerous collection of Newton's mathematical manuscripts scattered across Cambridge, and around the world, open up a new area of research. The study of the mathematical networks with which Newton interacted throughout his long and creative life. Indeed, the presence of text ranging from brief marginalia and interlineations to entire treatises written in other hands in the corpus of Newtonian mathematical manuscripts, which Newton clearly treasured as they formed part of his personal archive, reveal that he shared paper with other mathematicians. Now, there are several networks, and in this talk, I will focus on just two of them. I will therefore somewhat neglect the most important and frustratingly the least accessible network, the Cambridge network. You know, Newton lived in Cambridge with other mathematicians, and they didn't leave much trace of their interaction, actually. The Cambridge network was a network of mathematicians active in Cambridge, most notably Isaac Barrow. For obvious reasons, this network played a momentous role in shaping Newton's mathematical teaching and research. In my opinion, the two networks I've chosen for my talk are somewhat unjustly underrepresented in current historical account of Newton's mathematics, including my own. The first is the network of London practitioners with whom Newton got in touch via John Collins. I will introduce you to this mathematician very soon, in the 1670s. And the second network is the Oxford network of mathematicians committed in editing classical mathematical works. For example, John Wallis, David Gregory, and Edmund Halley, with whom Newton interacted after the mid-1680s. Studying the Collins network will help us to understand the aims and values pursued by Newton, the algebraist. Conversely, a study of the Oxford network will help us to define the aims and values pursued by Newton, the geometer. So the first network is relevant to study Newton's algebra. In a way, the second network is important for studying Newton and geometry. Before we begin, two caveats, so to speak, are in order. Firstly, it would be simplistic to pigeonhole Newton as belonging entirely to these networks, or to view him as being entirely defined by his membership of these two networks. He was in touch with them, which is often forgotten, but his approach to mathematics remained highly original, oriented towards the ambitious aim of mathematizing natural philosophy. Well, the program that Galileo realized, as Vincenzo recalled us before. Secondly, the two networks were not entirely separate. Some members could literally transition from one to the other by moving from Oxford to London and back again. For the sake of clarity, I will discuss them in turn, also because they occur in Newton's intellectual biography, somewhat in chronological sequence. So the Collins network. John Collins, born in 1627, died in 1683, was a scientific administrator in London. From 1642 to 1649, he served as a mathematician on board on an English merchantman engaged as a man of war in the Venetian service against the Turks. Upon returning to London, he held several administrative accounting posts. He is known to Newton scholars as one of the earliest mathematical correspondents of the newly elected Lucasian professor. I remind you that Newton was born in 1642. He entered Trinity College in 1661. He was elected Lucasian professor in 1669, a post he held for a long time. Then in 1696, he moved to London as warden and master of the Mint. Collins was instrumental in convincing Newton to revise a Latin translation of a Dutch treatise on algebra. The lack of updated algebra treatises available in England was one of Collins' main concerns. Thanks to his relationships with London printers and booksellers, as well as his extensive correspondence with mathematicians in Britain and abroad, he was able to facilitate exchanges between mathematicians and promote important mathematical publications. In recent years, Jackie Stedall, who sadly passed away a few years ago, Philip Bealey, and Guy Seacrest have devoted their attention to Collins and his network. More recently, Derrick Mosley, who was a postdoc in Milan for a while, has conducted pioneering research into the relationship between Newton and the so-called mathematical practitioners. Indeed, it was through Collins that Newton got in touch with several of these practitioners, accountants, land surveyors, gaugers, who worked for the excise office, l'ufficio delle accise, we would say, such as Michael Derry and John Smith. Contrary to what one might expect, Newton took this correspondence very seriously. He clearly showed respect for the London accountants and gaugers, as well as an interest in the issues they raised. These mathematicians needed methods to solve practical problems, such as gauging, calculating the volume of casks, producing numerical tables of square and cube roots, or tracing conics with the help of tracing tools. This is an example that one of the many examples I might make. This is a letter by Newton to Collins, which concerns a tracing mechanism for tracing conics that Newton devised. And he describes this tracing mechanism in very practical terms. He explains how to build it. And so we have two rulers. And the intersection of these rulers, of these two rulers, move along a straight line. And if this intersection moves along a straight line, the other intersection describe a conic section, in this case, a hyperbola. When we see things like that, we believe we can claim that Newton had a rather deep understanding of the projective properties of conic sections. And there are historians of mathematics who attribute to Newton an understanding of Steiner's theorem. It's very difficult to be a historian of mathematics because it is always, difficult to understand how mathematicians can anticipate results that solidified much later, so to speak. In any case, this is a beautiful example of what Newton shared with these people, very serious mathematics that turned useful later when Newton wrote the Principia. Mathematical practitioners, we all know, at least if we study Newton, we all know that in his early study of astronomy, Newton encountered the works of two astronomers, Vincent Wink and Thomas Street. And, Wing's Astronomia Britannica, 1669, and Street, Astronomia Carolina, 1710. Well, the second edition is 1710, but it is a work that was published when Newton was a student. Okay, these two works were, you know, Newton's introduction to Keplerian astronomy. But Wing and Street were, in fact, astrologers, land surveyors, and professional accountants, a fact that is often overlooked. Indeed, many of Newton's English contemporaries transitioned from professional practical mathematics and astrology, in Wing's case, to natural philosophy. They shared an ethos of professionals who were valued for their problem-oriented approach to mathematics, a mathematics of rules and instrument, if you will, and for their focus on numerical accuracy. They were obsessed with achieving numerical precision. When you work for the Ufficio delle Accise, when you work for the excise office, you have to be very precise. It is thanks to their competence as calculators and problem solvers that they approached astronomy and optics with the aim of developing their skills as number crunchers. In a sense, Newton shared their ethos from his correspondence with practitioners such as Derry and Smith, mediated by John Collins. One gets the impression that he considered himself part of their guild. And here I owe a debt to Miguel Onesorge for his comments on a paper I gave last May. Newton was, in a way, a problem solver. Yet, it is not without reason that Newton organized his primary treatise on fluxions, the so-called De Methodis Serierum et Fluxionum, as a series of numbered problems, each with a corresponding method of solution, followed by a series of numbered examples. So this is, you know, a page from a treatise on the method of fluxions that Newton wrote in 1670, 1671. And you see, he is asking himself a problem of quadrature, what anachronistically we would call a problem of integration. He has to solve this problem. He has a rule, and then he applies this problem to a number of examples. And, you know, another example is this one. This is a famous page from the so-called waste book. You know, the title is How to Draw Tangents to Mechanical Lines, we would say to transcendental curves. And Newton, you know, provides a number of examples, a spiral, an epicycloid, a quadratrix, incongruously an ellipse here, which is not a mechanical line, which is not a transcendental curve. But, you know, this is how Newton developed his early mathematics. As it is a mathematics of rules and you know, and problems, problem-solving mathematics, so to speak. So, when some of Newton's early manuscripts on the method of fluxions were published in a pamphlet entitled Commercium Epistolicum, etc., which was distributed for free in 1713, it is a pamphlet that was produced by the Royal Society to prove Newton's priority over Leibniz in the invention of the calculus. Many readers of the Commercium could only conclude that the early achievement of the president of the Royal Society, Isaac Newton, who had carefully edited the Commercium, lacked a clearly stated algorithm. And you know, this criticism that Newton's calculus of fluxions is less structured compared to Leibniz. Leibniz devised a notation, expressed rules, and organized his calculus in a much more systematic way. To many readers of Newton's early manuscripts that were at long last published in this pamphlet aimed to prove Newton's priority over Leibniz, many readers, well, from Johann Bernoulli in 1713 to a German mathematician, Thomas Sonner, who is the author of a well-documented book on the Newton-Leibniz priority controversy in 2016, Newton, the inventor of the calculus, appears inferior to Leibniz, who wrote much more systematic papers on the topic and had a much better notation. This happens, I claim, because Newton's presentation of calculus is a hands-on didactic approach, first addressed to solving problems that were asked, that were posed to him by the network of the mathematical practitioners, coordinated by John Collins. By behaving as a solicitous advisor for mathematicians employed in London as accountants, by writing on fluxions the way he did, Newton was conforming to the statutes of the Lucasian chair, which required him to hold office hours, 2 hours on 2 days per week during term time, in order to answer questions and problems from visitors, globes and other suitable mathematical instruments at hand. This was, you know, Newton, in the statutes of the Lucasian chair, Newton had to answer questions asked him from visitors. Newton's rooms at Trinity were not inhabited by a lonely mind, as Wordsworth might have thought. The statutes read that the Lucasian professor was required to maintain open access to all those who may visit his rooms. Even though the results of Halley's celebrated visit to Newton in summer 1684 was momentous for the scientific revolution, knocking on Newton's door with a mathematical question in mind is not to be considered unusual, for before Halley, the gaugers of the excise office, John Craig and John Flamsteed, had already done so. Failing to understand the culture of practical mathematics to which Newton belonged, if I may say provisionally and somewhat provocatively, failing to understand the tasks the mathematicians belonging to this culture set themselves, leads to misunderstanding, to historical misinterpretation. Typically, it leads to negative judgments, as we saw above, when Newton's treatise on fluxions is dismissed as theoretically confused. Clearly, I must moderate my exorbitant statements above. I repeated too many times that Newton was a mathematical practitioner, perhaps as a homage to Eva Taylor, who did indeed include Newton in her prosopographies on the mathematical practitioners in Stuart and Hanoverian England. However, I have exaggerated and oversimplified the matter. Newton's association with the Collins network only captures one aspect of how he portrayed himself as a mathematician. As a natural philosopher, Newton had other very ambitious aims, which he achieved with justly celebrated success. In the Prefatio ad Lectorem of the Principia, he stated that the whole difficulty for natural philosophers was to discover the forces of nature from the phenomena of motion and then to demonstrate the other phenomena from these forces. Newton was certainly not just a gauger such as Michael Derry. However, if we forget how deeply he shared the ethos of people like Collins and Derry, we fail to understand some of the aims and value that oriented his research on algebra and calculus in the mid-1660s and 1670s. Now, I move to the Oxford network. When dealing with London practitioners, I had to express my gratitude to Derrick Mosley, our talented postdoctoral researcher in Milan. However, here I must pay tribute to Giorgio Camillini, a young master's student of mine researching Newton's friend Edmund Halley, and to Philip Beeley, who shared his recently published papers on the Oxford editor with me. So I have to cite Philip Billey for both networks, actually. He is doing very excellent research in this field. Now, I turn to the Oxford network. Here you see two images of Wallis and Halley. Halley on the right, Wallis on the left. Halley was trained in Oxford and eventually became the Savilian professor of geometry in 1703. Oxford became home to a vast mathematical editorial project led by the holders of the Savilian chairs. This included Wallis, who edited Ptolemy's Harmonicorum Libri, right, Nathan? Aristarchus on the dimension and distance of the sun and moon, and a fragment of the second book of Papus Collectiones. And Archimedes Arenarius and Dimensio Circuli in 1676. Actually, Wallis, defined several ways in which mathematical manuscripts could be edited, actually. Another notable contributor to this Oxford project was Halley, who produced a renowned edition of Apollonius Conics, including the 5th, 6th, and 7th books based on Arabic manuscript, and reconstructed the 8th book. And his edition appeared in 1710. And David Gregory, who produced a complete edition of Euclid's work printed in 1703. So the Oxford mathematicians were deeply involved in translating and editing Greek and Arabic manuscripts, an endeavor that rivals the achievement of Commandino and Del Monte in Urbino a century earlier. And it is worth noting that the Oxford editors took Commandino's Latin translation of Greek authors, such as Euclid, Archimedes, and Apollonius, as the standards. So now I think I will skip 2 pages in which I describe the Oxford editorial project, in which emerged as a very important actor Edward Bernard. Edward Bernard is a very elusive contributor. He was, a monster of erudition. He knew Greek, of course, but also Hebrew, Arabic, and Syriac. And if you look into his manuscript, you find, Coptic and other manuscripts. Now, Bernard set himself the task, under the, you see, here we see Henry Saville here on the left, who endowed the university with an important, donation of books and manuscripts. And a century later, we have John Fell, a very important figure. But I see that the titles are not, you cannot see the titles here, but in any case, the guy on the right is John Fell, who raised to eminence in Oxford after the Restoration. And he commissioned Bernard the 21 volumes edition of the Greek works. Now, his work was resumed by David Gregory and Halley, who published their work. Now, we now return to Isaac Newton, who shifted his focus on to Greek geometry, and more specifically to Papus, Mathematicae Collectiones. It seems that he used the Manolesi edition that I have, that here I reproduce, the edition that it seems he used. And he turned to geometry in the late 1670s or early 1680s. Thank you very much for this. Oh, okay, but never mind. Leave it like that. So Newton turned to geometry. It stands to reason that Newton undertook this work in the context of his involvement in correcting Barrow's algebraized rendering of Euclid's elements. You know, Barrow had produced very early in the 1650s, but published in the 1650s, the elements, and in the 1670s, his work on Apollonius, Theodosius, and Archimedes. He had produced an edition of the Greek classics, in a way translated into algebra. So he was using William Oughtred's algebra in order to read the Greek classics in a way that is shorter. You know, the 15 books of Euclid's Elements are breviter demonstrati by Barrow. Here you can see a page of Barrow's Euclid, and you can see that Barrow, in a way, renders Euclid's reasoning in algebraical terms. And this is Newton's handwriting. This is Newton's copy of Euclid. And Newton, you know, applies very new symbols. This means A is to B as C is to D. And in this case, then A times D is equal to B times C. So it's a very simple thing. And because it is so simple, these, you know, commitment of the young Newton, we are in 1665 here, probably Newton, the young Newton is learning algebra and is writing things that are not, you know, the work of a genius, but you have to learn to do these things if you want to write the Principia. Yeah? Indeed, you know, Collins was preparing the publication of Barrow's Euclid alongside the works of Apollonius, Theodosius, and Archimedes, all of which were rendered by Barrow in the symbolic language introduced in England by Oughtred. An interesting fact showing the relationship between the Collins and Oxford network is that Bernard had planned to include Barrow's algebraic versions of the Greek classics in the footnotes of his mammoth polyglot edition. The extent of Newton's involvement in geometric research remained unknown until Whiteside's magnificent edition of Newton's papers. Remained unknown to us, but not to his contemporaries, because Newton shared his ideas on geometry with Gregory, with Wallis, with Halley. The Portsmouth and Macclesfield papers revealed that Newton shared his geometrical findings with Fazio de Duillier, David Gregory, William Jones, who disseminated them, ensuring that his contribution to the Geometria Veterum circulated within Newton's milieu. Newton turned his attention to the geometry of the ancients before writing the Principia, as evidenced by a notebook entitled Solutio Problematis Veterum de Loco Solido. When Newton writes the Principia, he has an amanuensis who writes for him, you know, a draft of Book 1 of the Principia. But if you look, this draft is a copy of the Solutio Problematis Veterum de Loco Solido, and Newton corrects what, you know, his amanuensis is doing, changing, you know, proposition to lemma, changing the title here, and so on and so forth. So Newton's research into the Geometria Veterum entered into the Principia, so to speak. But what was the problem that Newton, what was this problem of the ancients that Newton was interested in? It was Pappus' problem of 3 or 4 lines, which Descartes had feasured prominently in his Géométrie, that, as you know, Descartes added as an appendix to the Discours de la Méthode in 1637. And Descartes claimed that his solutions of the Pappus problem was a proof of the superiority of the new Cartesian algebraic method over the ancient geometrical method. According to Descartes, the ancient could not solve this problem. And this problem I lift this figure from a paper by Niccolò Guicciardini and Stephen Huggett, which I very much recommend. So, and I recommend also Niccolò Guicciardini's PhD thesis on Newton's geometry. So, given 4 lines, given in position, you can see the solid 4 lines are given in position, and corresponding 4 angles, find the locus of a point such that the angled distances from the point to each line maintain the constant ratio d1 times d2 divided, let's say so, d3 times d4. So you might think of these angles as 90-degree angles, if you like. So we have 4 lines given in position, and we look for the locus of points such as the distance d1 from point P to line 1 times the distance d2 of point P from line 2 is equal to a constant times d3 times d4, if you like. I'm not very rigorous here, but I hope. Now, if you know a little bit of algebra, you immediately realize that this locus is a 2nd-degree polynomial in x and y, and therefore it is a conic section. Because each di is linear in x and y, so you multiply the 2. Now, Descartes said, I solved this problem. I am better than Apollonius. Newton strongly disagreed. And here we see another manuscript by Newton, which is transcribed and translated here. To be sure, this is Whiteside's translation, the ancients' method is more elegant by far than the Cartesian one. For Descartes achieved the solution of the Pappus problem by an algebraic calculus, which when transposed into words following the practice of the ancients in their writings would prove to be so tedious and entangled as to provoke nausea. Nor might it be understood, but they accomplished it by certain simple proportions. Judging that nothing written in a different style was worthy to be read, and in consequence they were concealing the analysis by which they found their construction. Now, to comment this wonderful passage would require a whole paper, actually. It's very rich, a very interesting passage indeed. So, in Solutio Problematis, Newton provided a solution, a geometrical solution of Pappus' problem as presented in the Collectiones by Pappus, translated into Latin by our great hero, Federico Commandino. His solution relied on the instrument for tracing conics that I just showed you, which he had discussed with Collins in 1672. Pappus' problem is hardly a topic of interest to natural philosophy. However, Newton was so proud of having vindicated the ancients by showing that the Pappus problem could be solved using methods belonging to the Apollonian tradition that he included his solution in the Principia. And in the Principia, this is, his amanuensis writing a draft of Book 1. And when in the Principia Newton presents the solution of Pappus' problems, he adds that, that the problem is solved non calculus sed compositio geometrica qualem veteres querebant, not by an algebraic calculus, but by a geometrical construction as the ancients required. Now, it could be argued that Newton's success hinged on his reading of Apollonius conics with the aids of Barrow's algebraic interpretation. So if I ask Nathan what he thinks about Newton's solution, he would say that it is very remote from what Apollonius might have done. But for Newton, this was a vindication of the ancient. Newton's divination of the methods of the ancients was more modern than he would have liked to admit. No doubt, the members of the Oxford network of editors of ancient mathematical works were impressed. During his week-long visit to Newton in Cambridge in May 1694, David Gregory, a Scottish mathematician, he was an Episcopalian who moved to Oxford in order to find a more hospitable environment for his political views, and he was the head of a group of Newtonians that Anita Guerrini, in a seminal paper, dubbed the Tory Newtonian. Now, Gregory reported in his memoranda on the breadth and depth of Newton's achievement in restoring the geometry of the ancient. He informed the Oxford group, John Kyle, for example, John Wallis, that Newton intended to add an appendix on the geometry of the ancients to a planned second edition of his Principia. Indeed, one of the Oxford editors was to complete and perhaps even surpass the work of the ancients. They took the geometric methods of Euclid, Apollonius, and Archimedes very seriously as a research topic. Geometry, the old method, was still an open area of research, just like the new fields of algebra and calculus. Mathematical prowess was required for editorial work, partly because editing a mathematical text required the ability to fill in the gaps, a skill that only a practicing mathematician can possess. Several decades later, John Colson, one of Newton's successors on the Lucasian chair, this John Colson, a Lucasian professor, not the most important to hold the chair, captured the prestige that Newton's skills in interpreting ancient texts could confer upon him when, in a letter dated 20 September 1737 to William Jones, one who left a trace in the Portsmouth paper and was at the origin of most of the Macclesfield collection. When John Colson, writing to William Jones, defined Newton as our great restorer and improver, Isaac Newton. Newton was perceived as an innovator as well as a rediscoverer of past truths, and not only in the field of mathematics. During the period when he turned to the study of ancient geometry, Newton also began researching prophecies in Holy Scripture and the history of the Church, area of study typically pursued by scholars such as Henry Moore. The way he worked with paper and ink and the growing size of his library show that he was slowly redefining his persona and becoming involved not only in research related to mathematical editorial projects, but also in scholarly work in divinity. Newton's library grows in this period, at the end of the 1670s, and his way of organizing his archive changes in ways that I will not describe now. The extent to which Newton became committed to erudite pursuits is revealed in a cartouche in Logan's Cantabrigia Illustrata, 1690. This cartouche was identified by Stevens Dobelen, and I very much, I'm very, very grateful to him for drawing my attention to, we can see here the Church of Great St. Mary, and a dedication to Newton, which sounds as follows in translation: to the most distinguished and most learned man, Isaac Newton, Lucasian professor of mathematics at Cambridge, fellow of the College of the Most Holy Trinity at the same place, fellow of the Royal Society, most accomplished mathematician, philosopher, because he has written he has published the Principia, and chemist, because Newton was known for his practice of alchemy. No less admirable for his agreeableness of manners and integrity of spirit, together with his skill in matters human and divine, in the human sciences and in theology. David Logan thus gives, dedicates, and consecrates this print for veneration. Dat dicat consecratque David Logan, yeah. Here, Newton is celebrated not only as a mathematician and natural philosopher, but also as a chemist and for his competence in the humanities, including history, chronology, and biblical hermeneutics. The relationship between mathematics, history, and divinity was not unusual at the time. It is very often the case that we think that Newton was crazy, was strange. But we should not view the scope of Newton's pursuit as revealing the contradictory nature of the genius, the genus phasis of genius, to use Dobbs' title of a famous book, with a secret side that was only revealed to the world when his manuscripts were sold at Sotheby in 1936. Newton's commitment to divinity and the humanity was well known and unsurprising in a culture where a mathematician, a Savilian professor of astronomy, such as Edward Bernard, I skipped the pages devoted to him to keep with time, could edit Josephus. He edited Giuseppe Flavio, Jewish antiquities, for example, and he began a translation from Arabic into Latin of the last books of Apollonius Conix, a manuscript that he was able to obtain after traveling to Leiden. And he died because of this. He got ill and he died in the process of obtaining this manuscript. Newton's commitment to divinity and history was not the result of a U-turn from mathematics or a rebellion, as Westphal would put it. It baffles us as 20th and 21st century historians of mathematics simply because we have paid little attention to the disciplinary boundaries in place in Newton's milieu. As Jed Bachwald and Moti Feingold have amply demonstrated, mathematics, biblical exegesis, and chronology were related discipline. It is just, you have just to read Robyle's book, Newton, Priest of Nature, to be convinced about that. At this juncture, before coming to a conclusion, and as I've done in concluding the section of the Collins Network, I must add a caveat and reflect with you on a misunderstanding. The caveat has a similar structure. Just as it would be excessive and oversimplifying to define Newton as a practitioner a la Collins, so it would be excessive and oversimplifying to define him as an editor a la Bernard, let us say so. Newton was never a philologist capable of or indeed interested in editing Greek, not to mention Arabic mathematical works. Nevertheless, Feingold's research shows that Newton's advice on the publication of Barrow's algebraic renderings of Euclid, Apollonius, Theodosius, and Archimedes, requested by Collins, warrants greater consideration. Newton's interest in and engagement with ancient geometrical text was primarily driven by a creative mathematical project. As Vincenzo De Risi, a Del Monte medalist, recently demonstrated in a wonderful paper which is in print, this project involved extending Euclid's postulate to solve higher level problems such as dissecting an angle or constructing the 3 or 4 lines locus. According to Newton, the solution had to be geometrical due to the advantages of geometry over algebra. As he often insisted, geometers never lose contact with the objects they are dealing with, always visualize their reasoning, and their proofs are simple. As with the previous section on the Collins network, the misunderstanding is rooted in our misreading of Newton, which occurred when we failed to take into account the social dimension of his aim as a mathematician. One might argue that while Newton's geometrical solution of Pappus' problem is effective for 4 lines, it cannot be generalized. In contrast, Descartes' algebraic solution can be applied to any number of lines. d1 times d2 is a polynomial of 2nd degree, d1 times d2 times d3 is a polynomial of 3rd degree, and so on and so forth. So you have solved the Pappus problem for any number of lines. And so it is often the case that Newton's solution is contrasted to Descartes' solution, and it is considered less satisfactory because it is not generalizable. So what is the significance of Newton's achievement he was so proud of, which he proudly included in the Principia? This is an interesting criticism. Karin Shemla, my predecessor as recipient of the Commandino Medal, taught us that the value of generality is culturally situated. This value has not always had precedence over other values in all mathematical cultures. Newton's case confirms Karin's thesis. Newton was willing to give up generality in favor of the values he believed the geometry possessed: simplicity, elegance, continuity with the ancient traditions, ontological content, visualizability. Each of these values and the role it played in Newton's thought would deserve, many, many, many pages. Perhaps we should also mention that he belonged to a mathematical culture that valued the restoration or divination of ancient works to an extent that is unthinkable today. In fact, we have misunderstood Newton's intention. So the last 5 minutes are devoted to some concluding remarks. We have seen that according to the memorandum by David Gregory dated May 1694, when speaking of the relationship between algebra and geometry, Newton preferred the following evaluation: algebram nostram speciosam. I will not tell you what speciosam means. Algebram nostram esse ad inveniendum apta satis at literis posterisque consignandum prorsus ineptam. Since the 1680s, Newton had dismissed algebra, the method of fluxions as well, as merely heuristic methods that were useful for finding it out. Ad inveniendum, apti, these 2 methods, apte, these 2 methods, and thus useful for answering Collins' practical questions. However, he believed that they should be avoided in public communication. I correspond with Collins, I use algebra, but if I have to express myself in public, I have to be a follower of the Greek. Unlike the methods of the moderns, of the recentes, which was doomed to elicit controversy due to its use of questionable concepts such as infinitesimal, or the roots of the negatives, for example, the geometry of the ancients, of the veteres, could gain the assent of his intended readers. This was a vital requirement for a natural philosopher who aimed to inject certainty into natural philosophy by avoiding the conjectures and probabilities in vogue at the time among Cartesian and Baconians, and doing so through mathematics. Newton wanted to construct a mathematical natural philosophy that could overcome the conjectural and debatable status of Cartesian and Baconian natural philosophy. Geometry is ontological founded and refers to objects that have an existence in rerum natura, as Newton wrote, and are always visualizable in contrast to algebra. Geometry offers simplicity, elegance, and certainty, and is grounded in an ancient tradition. Newton's aims and values differed from our own. As historians of mathematics, we should recognize that mathematicians of the past asked different questions, set themselves different tasks, and had a different understanding of the disciplinary status of mathematics. We should recognize the otherness of Newton's present, to borrow Giulio Preti's phrasing, who once warned us that the past of the historical actors we study is un altro presente. L'oggetto della scienza storica non è il nostro passato, ma un altro presente. An ideal for historical studies that is captured also by my PhD supervisor, Ivor Grattan-Guinness, who distinguished between heritage of mathematics and history of mathematics. In my talk, I focused on the social dimension of Newton's mathematics. I have attempted to contextualize his mathematical research within two of the networks he was involved with. What have we gained by doing so? I claim that we have gained a better understanding of the aims, values, and disciplinary boundaries that shaped his work. Such historical awareness of the otherness of Newton's culture enables us to avoid making negative judgments about his mathematics, which are, in a way, misunderstanding of his mathematics. In the examples I presented, his work might appear to be that of a mere problem solver whose results lack systematicity or generality in the case of Pappus' problem. These negative evaluations, our conviction that there are obvious shortcomings in Newton's mathematical work, stem from our inability to distance ourselves from the grand narrative of the discovery of the calculus as part of the development of pure mathematics. To practice the history of mathematics, we should try to place this epistemically robust discipline, because mathematics is epistemically robust, and the history of mathematics displays a great continuity through time and across culture. There is no doubt about that. The results of mathematics are transmitted successfully across geographically and chronologically distant culture. But as historian, we should place mathematics into a local context. The tension between the undeniable universality of mathematics, a universality that makes a purely internal history of mathematics perfectly feasible. There are very good internal history of mathematics. So the tension between the undeniable universality of mathematics and its cultural situatedness is a constant source of interest for me as a historian. 40 minutes. No, 60 minutes, sorry. 60 minutes. 60 minutes. So thank you very much.